Hello, everybody, and welcome to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about global systems of pressure and wind. In the last video, we talked about what pressure and wind are. Wind is really just that horizontal expression of differential pressure, or the pressure gradient force, which is also impacted by things like the Coriolis force, and at the surface, frictional forces, which is not the case at winds aloft. So first off, let's review controls on global surface air temperature patterns. We have latitude, elevation, land and water thermal contrasts, ocean currents, and atmospheric circulation patterns. We may recall from our atmospheric pressure and winds lectures that pressure is just the average force per unit area exerted by the overlying atmosphere. Wind is the horizontal expression of differences in atmospheric pressure, which is caused by things like differential heating of the atmosphere and changes in speed or direction of winds aloft. And forces that affect wind include the pressure gradient force, friction force, and Coriolis force. In the case of a low pressure system, the pressure gradient force is towards the center of the system, the zone of lowest pressure, while the Coriolis force leads to the rotation of the system, and the frictional forces oppose that movement. We generally see this as a counterclockwise rotating system that looks something like this. So here we have a converging winds at the surface, a low pressure system at the surface, diverging winds aloft, and a high pressure system aloft. In high pressure systems, we see those winds deflected outwards by the pressure gradient force in a clockwise direction, which looks like this. So you've got diverging winds at the surface because of converging winds aloft and descending air aloft as well. Now, as is often the case, Earth is not a perfect system, and the differences in pressure across the planet are caused by a myriad of different things. Now, that's not to say that there aren't patterns involved in that pressure setup across the world. For example, we notice something going on here, right? Or so right around the equator. But we also notice different trends, things like cyclogenesis to the north and to the south, as we watch these different systems kind of rip and move across. But there are patterns to this global system of pressure and wind. And that's where we're going to go next. So now we're going to look at some of these global systems and these global patterns that drive meteorological phenomena across our planet over, for example, a given year. So here we're looking at a mean sea level pressure map in January of the year. There is a whole lot of different things going on. We see a series of different named pressure systems that exist because they are so consistent throughout a given year. Things like the Aleutian Low or the Icelandic Low or the Siberian High, which sets up over the Eurasian continent, or the Bermuda Azores High. We notice that there are trends of low and high pressure systems dotting all over the world. And those aren't the only ones. These are just a few of the ones that we're looking at here. Now, we also notice the intertropical convergence zone where we have, and we'll talk about it in, I think, next week's lecture, these kind of global other atmospheric global patterns. But here we've got converging winds. So here we've got kind of this consistent low pressure system. Now, in July, it looks strikingly different. The Bermuda Azores High is here. The Hawaiian High takes over. We don't see that low pressure system setting up. So we've got kind of this incumbent high that just sets over the Hawaiian Islands area and Gulf of Alaska and the coast of British Columbia and the Pacific Northwest. We've got a Tibetan low pressure system that sets up over here. And again, some other unnamed ones. We see these high pressure systems setting up over the continents, down in South America, or not South America, down in the southern hemisphere, pardon me, during the winter, the astronomic winter for these regions here. Whereas we see some of these low pressure systems setting up over summer in the northern hemisphere. So let's talk about some circulation models first. Well, the first one is what we would call a single cell circulation model. This was first posited by George Hadley in 1735, saying that large temperature contrasts between the poles and the equators create large convection cells in both of the hemispheres. So let's think about how circulation would work in a room with a heater and a window. The heater is providing heat. The window is providing cooler air. You can see those here. Obviously, there is a temperature gradient between the hotter air around the heater and the colder air around the window. That hot air, as we know, rises because it is less dense. And as it cools, it can maybe move horizontally. And as it cools, it descends. And then it cycles back. This is a similar concept between the equator and the poles, at least in the single cell circulation model that we see here. In this, we've got one large Hadley cell, as it's named, between the warmer equatorial zones and the colder polar zones. And this cycling between cold and warm is what generates some of these dominant pressure and wind systems. Now, we know that's not really the case. There's another model, a three-cell circulation model proposed in the 1920s to incorporate rotational forces. Now, the term Hadley cell was kept in honor of George Hadley, but it's now used to describe a zone between about 30 degrees north and south and the equator. The Ferrel cells were proposed by William Ferrel to account for the westerly surface winds in the middle latitudes, and polar cell circulation was driven by subsidence near the poles that drives surface winds towards the equator. Let's see what that looks like here. Here we can see that idealized diagram of the whole system. So we're going to pick apart each of these to kind of better understand how this system functions. But we can see a few different things. We see the equator at 0. We see the intertropical convergence zone right here. We see these Hadley cells that are setting up between 0 and 30 north and south, the Ferrel cells between 30 and 60 north and south, and the polar cells between 60 and 90 north and south. What this leads to is predominant high and low pressure systems across the planet. So let's start off with the low latitudes. So here we're going to look at a side view of the troposphere in the low latitudes between 30 degrees north and south. Obviously, we have much warmer winds around the equator. So we're going to look at a point at about 500 millibars of atmospheric pressure. Now, if we were to look at that same point over 30 degrees north and south, we'd see that we kind of have this bowed effect. Because you have warmer air and a vertically displaced pressure level, because dense or less dense air, by the time you get to that point, it's a little bit higher up in the atmosphere. By 300 millibars, we see that it's even more pronounced. So here we've got these high pressure systems as air is kind of converging at the surface and rising up here. Pardon the lack of straight lines that I'm drawing here. So we have this high pressure system that sets up over the equator, kind of cycling winds to these low pressure zones, which we see here. And once you get to those low pressure zones and your air has cooled, it begins to descend. So as that air descends, it gives rise to these high pressure systems at about 30 degrees north and south. And as we recall, air warms adiabatically as it descends. So about 30 degrees north and south are where we see some of the most dominant deserts across our planet, because we have this warm air that's descending. And as it warms, it's basically dry. And we see these desert formations right around 30 or so degrees north and south latitude. But the trade winds, which are driven by the equatorward flow that is deflected by the Coriolis force, we'll see a picture of these here in just a second, are so called because they enabled early sailing ships to move goods between Europe and North America. In the northern hemisphere, they blow from the northeast, while in the southern hemisphere, they blow towards the southeast. They converge near the equator in a region that has a weak pressure gradient. This zone is referred to as the doldrums. Here we can see our trade winds here. The doldrums basically just refer to an area where light winds and humid conditions provide monotonous weather. Then we have our intertropical convergence zone, which just refers to the low pressure zone where the trade winds converge. Now, typically we see this, as we saw in that image before, as a band of clouds. So you've got all this air rushing towards the doldrums. It's very moist at this point, and as it kind of converges and air rises, it rises and cools, condenses, you have cloud formation. You can see the cycle continues as that warm air in the equator rises again. So this is what we call our Hadley cells, right? Now, bringing in a little bit of what we learned in our last series of lectures. So warm rising air at the equator releases latent heat during the formation of large cumulus clouds. And this is basically what's thought to provide energy to drive this Hadley cell circulation. So as upper level airflow moves away from the stormy equatorial region, radiation cooling dominates. Furthermore, recall that the Coriolis force strengthens with distance from the equator. Poleward moving upper air is deflected into nearly west to east flow by the time it reaches about 30 degrees latitude, restricting the poleward flow of air. The air subsides between about 20 and 35 degrees latitude and is relatively dry because much of that moisture was released near the equator. Adiabatic heating, as we've talked about earlier, dries the air even more. And again, as I said, we think of areas like the Saharan deserts, the Gobi deserts, the desert southwest in the United States. All of these areas line up with this subsiding air that's been adiabatically warmed and dried. So our major deserts across the world. Now we can see here, this is something called the Köppen-Geiger climate classification system. Now we're not really going to dive into it here in this class. This is more for a class on climatology, something like Geography 340, which I teach in the fall. But here we see that right around 30 degrees, 20 to 35 or so degrees north and south latitude, we see those dominant deserts lining up pretty well. So here in this example, we can see our equator outlined here in blue, roughly about 40,100 kilometers in circumference. We have 30 degrees north latitude in this example, since we're looking straight down from the North Pole, roughly about 34,700 kilometers in circumference. And we've got this air that's rushing in from the equator to these low pressure zones from the high pressure aloft at the equator. And based on that Coriolis force, we see winds being deflected here towards the right in the northern hemisphere. So based off of this consistent, now we could imagine these arrows, the ones coming from the equator towards the pole, we could consider these to be completely around the globe that we're looking at here. This leads to what we call the subtropical jet stream. This is really important. It's important because our subtropical jet streams, which function at roughly 30 degrees north and south, lead to some pretty consistent trends in winds aloft. Now, these aren't the only patterns that are functioning within our low latitudes, our 0 to 30 degrees north and south. So we have our trade winds at the surface. We've got this cycling air at 500 and 300 millibars, these high pressure diverging conditions, obviously. But then we've got something called the trade winds. So we've got this wind rushing in from the high pressure systems at 30 degrees north and south towards the low pressure system that is the equator at the surface. And as it's rising, we've got this smaller circulation cell that occurs. Now, a trade wind inversion refers to a characteristic temperature inversion usually present in the trade wind streams over the eastern portions of the tropical oceans. It's found in large-scale subsiding flows constituting the descent branches of the Hadley cells. So these exterior branches where this colder air is descending and piling up at the surface. So you'll get this temperature inversion that occurs that you can see over places like, or around places like Hawaii, for example. So there we can see these are our trade wind inversions right here. Now we're going to move up to our mid and high latitude systems. All right, so now we're going to walk through another diagram here. So this is a side view of the troposphere in the mid and high latitudes between about 30 degrees north and 90 degrees north in this example. So we've got our subtropical high here. We can recall our subtropical jet stream there. Descending air aloft, dropping down to the surface, this high pressure system at about 30 degrees north latitude. So we've got air diverging from the surface in both directions, so towards the equator and towards the pole. So those are what we call our westerlies. Now, there's a difference in kind of temperature gradient between the poles and the equator, or really 30 degrees north, that we call the polar front, right about here. So the circulation in the polar cell is driven by subsidence near the poles that produces a surface flow that moves equatorward. Let's see, like this. We call those our polar easterlies, and we call them this in both hemispheres. So as that cold polar wind moves towards the equator, they eventually encounter the warm westerly flows of the mid-latitudes. You can see our system here. The region where that flow of cold air clashes with the warm has been named the polar front, which is where the most prevalent jet stream occurs. So notice the difference here because this is a front in pressure from one side to the other. Same thing here, it's even more prevalent at altitude. You can see if we're going from 500 millibars, for example, it's a pretty steep drop off as you encounter that polar front and move towards the poles. Same thing here. We notice, so that's going to lead to a much steeper pressure gradient force moving from one side of that polar front to the other. Right here, that's our polar jet stream. So as the polar jet stream moves towards the equator in the winter months, it can bring deep, cold, plunging troughs from this jet. You might recall a number of years ago hearing the polar vortex being thrown around in the media. That's basically what we've got going on here. This was caused by a polar jet that was relatively entrenched or kind of unmoving for a period of time as it kind of descended into kind of the mid-tropics, or not mid-tropics, mid-latitudes from its typical position, maybe around 70 or 65 or so degrees north and south latitude. So in this zone, we've got a low pressure system that's being filled by these polar easterlies and polar westerlies diverging from their positions, converging in kind of that mid-latitudinal region. We call that our subpolar low. So here we can see an image of our globe. And here we can see those typical features here. So we've got our low pressure system at the surface, the intertropical convergence zone, which we see in that red dashed line, diverging air aloft, moving kind of poleward, converging air at the surface, moving equatorward, the Coriolis force deflecting these winds, the trade winds. We see our subtropical highs. And this is how the system kind of sets up. So as we move forward, we've got our easterlies and our polar high pressure systems, and our polar fronts on both the north and south hemispheres. And these move with the seasons. Here we can see this would be winter in the northern hemisphere because that polar front has dropped to about midway through the upper Midwest, which we often experience as these really cold days. That if we have a very highly meandering polar jet stream, so draw a quick image here. So if it's shown in this nice idealized diagram here, but a lot of times it'll be moving and meandering like this. Now, if you have, because we've got these meridional winds and that are moving primarily north to south, this plunging air from the Arctic Circle or upper latitudes can bring this really cold air down. So what we experience is those really, really dry, cold days in January and February where it's 30 below out Fahrenheit. Although, fun fact, Fahrenheit and Celsius cross at 40 degrees, negative 40 degrees. So 40 degrees below Fahrenheit is the same as 40 degrees below Celsius. They feel the same at that point. And I felt that because of this polar jet bringing this cold plunging air down. You can see that here. Here we can see these kind of low pressure troughs and kind of how wind functions in these areas. So this cold plunging air or wind or air being brought up from kind of the Caribbean and mid-Atlantic. So let's talk about a few of these semi-permanent systems here. We can see them here. We talked about them before, that Aleutian low, the Siberian high, the Canadian high, and the Pacific high, the Icelandic low, and the Bermuda high. We talked about these briefly at the start, the onset of the video here. So what we're looking at is these kind of semi-permanent systems, pardon me, in January. At 500 millibars, these are the streamlines and isotherms in January as well. You can kind of see low pressure systems setting up over Greenland and kind of northern Canada, over northern Russia as well. These high pressure systems setting up over kind of Brazil into Africa and off the coast of Chile as well, and Peru, and then kind of south of India as well. In July, we have our Pacific high. We've got a thermal low that sets up over the desert southwest of the United States. We have our Icelandic low. We've got another thermal low that sets up over kind of the Tibetan Plateau area. And here we can see that that high pressure system moves north. So kind of the over maybe around Hawaii, over the southern US and Mexico and northern Africa. And then just a couple of quick words on our jet stream here. So we talked about it, but to define it, jet streams are these relatively narrow bands of really strong winds in the upper levels of the atmosphere. So these are winds that blow from west to east in jet streams, but the flow often shifts to the north and south. Jet streams follow the boundaries between hot and cold air. So since these hot and cold air boundaries are most pronounced in the winter, jet streams are the strongest for both the northern and southern hemispheres in their appropriate winter months. So December through February for the northern hemisphere, and June through August or so for the southern hemisphere. The actual appearance of jet streams results from the complex interactions between many variables, such as the location of these dominant or semi-permanent high and low pressure systems, warm and cold air, and seasonal changes. They meander around the globe, dipping and rising in altitude, latitude, splitting at times, forming eddies, and even disappearing altogether just to appear somewhere else. Jet streams also, we could say, follow the sun, in that as the sun's elevation increases each day in the spring, the average latitude of the jet shifts poleward. By summer in the northern hemisphere, it's typically found near the US-Canadian border. As autumn approaches and the sun's elevation decreases, that jet stream average latitude moves towards the equator again. Again, that's how we feel these kind of plunging Arctic air in our winters. So here we can see an example of the jet stream at about 500 hectopascals, moving kind of over maybe the Irkutsk region in Russia into Alaska, kind of having this big high pressure system setting up and a low pressure system that's setting up just north of Hawaii. And we can see it's descending, and kind of by the time it's moving over the United States, we have these kind of geostrophic zonal winds. So zonal winds meaning they're moving kind of just directly west to east, kind of bringing this kind of maybe humid air into the Vancouver, Seattle area, kind of moving eastward across the United States and Canada. So that's all for this video. Here we talked about circulation models, low, mid, and high latitudinal trends, semi-permanent pressure systems, and our jet stream. So in the next set of videos, we're going to look at more of these atmospheric patterns and ocean circulation patterns, things that, aside from just pressure differentials, really drive the variations and variability of meteorological phenomena across our world. So I hope you enjoyed that video, and we will see you in the next one. Thanks.